My name is Kamiński. I work for CodeWise. Today I would like to tell you more about the small library we've created after we had troubles with communication between microservices. And so this is a story about getting stuck on the gigabit highway. And let's start. Uh, so the first part of the presentation will be wrapping up the information that you should already know. And want to give you some background because the first time I gave this presentation, people were a bit confused. What's the vocabulary, domain, and stuff like that. So I want to go quickly through the first part of the presentation, and then focus on the what we actually did. Uh, so microservices. And you probably want to use microservices to measure your organization hierarchy and scale services independently. You want to allow different life cycle of each service. You want to allow different coding style and technology stack, right? And you would like to probably force some compartments and define fallback scenarios when facing failures. And I think the most important about microservices is to hide complexity, to define clear interfaces between services, and I think that's all clear. There are many conferences that talking about that. And so I've joined Volume DSP, and DSP stands for Demand Side Platform. So we are in this area. So we connect advertisers with ad consumers, and we receive requests from SSPs. We call it ad exchanges, and for each request from such SSP, we are choosing best ad and we are sending it back. So it all started in 2015, and I joined the company. We created a team consisted by 4 people, and the goal was simple. So goal was to handle 1 million requests per second. So I don't know what's your scale and how big traffic you can handle, but that was the goal, and we were like uh, crazy and how we are going to do it. It was nobody had experience with such traffic, and the second goal was to handle each request within 100 milliseconds, because this is the requirement that's set by ad exchange, and if we cannot deliver a response, they will just skip this request and reject our response. And so this is the initial sketch, and so that's the background for you to visual. I would like to visualize how we envision this project, those microservices that are connected, and they need to do some work. And I think that we already had some experience with microservices. We know how to debug, how to collect metrics, how to collect logs, how to automate stuff, how to troubleshoot, and all this stuff. But so that's the very simple overview, and we decided that we are going to create the first level, so-called traffics, and they are just decoding and coding JSON payloads from the internet, from ad exchanges, and they are translating those requests to our internal model that is a bit more compact. The second layer is bidders themselves, and they are core of the application, and bidders they hold all the data, also the ads themselves and the information about the ads, and they can make decision whether to bid or not. Uh, Third service was so-called wallet. So wallet keeps track of the all transaction and can reject ad if client that owns this ad broke some limit, and we cannot allow him to bid anymore. Uh, so so the only thing to figure out was to how to connect those services to cope with the requirements. And no-brainer was that we probably need some secret breakers. We need a long-living connection between those services, because we cannot afford on creating new connection each time. We need some internal routers. We want to have some non-blocking API, right? So we've chosen NetIO, and I don't know how many of you are using actually NetI. Okay, a few of you. All right. So we've chosen NetI because it promises clear separation of concert. And it's actually the copy paste from the page, and they have blocking, non-blocking APIs. They promise to have a very nice threading model, so we were hooked. And actually we were hooked mostly by the benchmark we saw on the internet, and they were beautiful. So having in mind that we need to push 1 million requests per second, we decided, yeah, okay, that's our thing. So for you that never worked with NetI, I would like to just quickly walk through some code and some overview to give you a feel how it's using NetI. So basically, you're using some simple builder. You can decide how many threads you're going to use by defining the thread group. You can configure various implementation of connections, and then you can decide what's going to happen on each connection that you receive by your server, and then on each and what steps are going to be executed uh, for each request. So Netty has those building blocks that are connection, and then the pipeline that are steps for the pipeline defines steps for each request. Client is very similar. You again have a builder. You need to specify your thread group, and then again you're instructing Netty what to do for each request. So how handler looks like? You're extending a channel handler, and then you have and channel handler can work with your own domain. You have access to context, to channel context, so which is created for each connection. And then you can, with this channel context, you can interact with other handlers, and you can decide whether to respond something, or maybe to push data to next handler in pipeline. So it's okay, it feels simple. And so to reiterate, we have this thread group that Netty calls event loops, and I will go to the details in a second. And we have connections, which are called in the Netty channels. Channel has reference to the pipeline. Pipeline defines steps for each request, so handlers A, B, and C. The rules the rule for Netty is that the channel is owned by only one thread, and thread can own more channels like this. So there is no interaction between threads. If one thread started to execute the request, it will execute the pipeline to the end when the response is sent back. So it's very simple but efficient and powerful concept. And let's see this in action. So we have the uh, event loop that owns the channel. You have the buffer, you have the pipeline, the steps that will be executed for request. You have the special queue by which other threads can communicate with this thread. So once there's something in the buffer, thread is getting this data, is executing pipeline, get some response, and write it back. Meanwhile, other threads were adding something to the queue, and now there is nothing to do for this event loop, and it grabs those tasks from queue. The task can do whatever it wants, so it can write something back to the channel, or maybe I don't know, there's some the task that is not related to IO, and that's it. There is again data in the buffer, so we start all over again. That's why it calls event loop. And to give you some also idea how performant net is, those are benchmark, and I designed those benchmark to actually do something. So I don't try to fool myself and return over and over the same data. So this benchmark was run in the same availability zone on Amazon Cloud, and I got like 10 gigabit network between those machines. They were like 4 cores and a gigabyte of RAM. So in this example, the server running the client use only one thread to backing connection, and on the server side also there were only one thread for this connection, and this thread was executing all logic, and I was able to push 10 million messages in around 16 seconds, and so it's like around 600,000 requests per second, which is quite good. To That's the histogram of the latencies. So you can see that most of the responses were back below 1 millisecond, and that's fantastic, right? And probably if we have 4 cores, we would like to scale this benchmark. And so now we have 4 connections backed by 4 threads on the client side and on the server side. So I was able to push 10 million message in around 9 seconds, which corresponds to 1 million requests per second, which is huge. And of course, the latencies are a bit worse, but because of each thread now is pushing only 2.5 million rather than 10 million, we got this improvement. And this is just the comparison. This is the first benchmark with only one thread, and those are the best and the worst charts from the second one. So it's not that bad, right? And there are some issues with some thread, but they are not that bad. And overall, we got some improvement. We were able to push those 1 million requests per second. So getting back to our business, and so in 2015 it looks simple, right? There was only traffic, bidders, and but then we got some requests for features, and we realized that we cannot squeeze all data to one bidder. So we started introducing new specialized services to the fast path, right? So now we have a lot more, and those machines collects data like black list, white list, IP list, how frequent the ad was displayed, fraud, optimization, loyalty, and stuff like that. So In 2016, we ended with 10 downstream connections to services, and we had to make all calls to all those to those services, and we couldn't make this in parallel because each service could decide that doesn't want to proceed with the request. So instead of just flooding all the services, we decided that it's better to just call one. If it agreed to proceed, we are going to call next. So we need to now call 10 microservices, still respond in the 100 millisecond, and I think it's crazy. So the problem, the problem is that we stop processing, and so that's actually the presentation, the problem I want to talk about, and how we solve it. And the key thing is that we start seeing that our circuit breakers they stop communication, but not only on traffic level, but also within the bidders, which is even weirder because if it was only on the traffic, so that would mean that there is something going on between bidders and those downstream services, and they have not enough performance, so we are timing out on the traffic. But actually, on the bidder side, also we saw that we got timeouts, floods, and other errors. And we made various tests, and we verified that each service, each application is perform very well. So there is no issue with that. So now I will show you that what's actually the reason. If you remember this overview that you have the service thread group, loop group, and they are operating on the pipeline that are synchronous. Everything's great. Netty knows how to do it, and basically that's what you're going to see in each documentation. And so those examples are very simple. But once you're starting adding some asynchronous job, and by asynchronous I mean, for example, a client that doesn't block the calling thread, then as I show you, things are a bit uglier. So let's go back to the example. I want to now from bidder I want to call another service, and I'm specifying I need to specify a thread group that will be executing the client pipeline. So I can pass the pipe the service event loop group, but actually doesn't matter. We can create new one only for this client. So if I add a client to the picture, now I need to share this client with other threads, and now handler B runs once by the blue, once by orange thread. Now it's calling client, and is executing the client's pipeline, and it's passing the it wants to asking to the client to do the job, and needs to await for response, and and you need to await for the response in order to resume the callers the service pipeline to get to the handler C. So now the question is, which thread is executing handler C? And that's the biggest question. And so the one here, right? We got some response from client here, and then we want to resume this pipeline. The answer is that it depends, and if you have access to caller channel the context, as I show you at the beginning, then you probably will be fine, and you can just use the context of the channel, and just pass the response from the client to the caller's pipeline, and Netty will figure out which thread to use, because context is bound to the thread. Or you don't, and you don't. So you can probably, to await for the response, you're going to use probably computable future, which is a very popular choice in Java world. And probably you are going to use then apply API of the computable future. But actually, you want to use this API, then apply async, and then you can specify which executor we're going to post-process the data, the response. But again, you probably would like to use the context thread, the event loop that is running the caller's pipeline. And again, you need to have reference to the context. If you don't specify this executor, you have no idea who's going to probably the client thread will execute the handler C. So all in all, it's it's about threading, but this time it wasn't. You know, for many years you were struggling with threads, with synchronization, and you realize that you're doing wrong. Here it's more about interaction. So if you messed up and now your handler C is not very complex, is doing some short logic, you can get away with it, right? And probably we were lucky for almost 2 years that we were keep adding new clients, new handlers, logic, and that was fine, and nobody realized that we are doing something really stupid. And so the bottleneck again is not the performance of a particular service, but it's this little client thread, or the thread that is supposed to only do the communication logic, and now it's forced to execute the handlers in the pipeline of the caller. So it's doing much more that it's supposed to do, and so it's not really a problem of the Netty itself, right? It's a problem of microarchitecture, and probably we could be more careful. And so, but there are other problems with Netty if you're using Netty as it is. So Netty is in Netty it's hard to route business events. It's if you need access to context everywhere, then you know just mess Netty with your domain, and you don't want to do this. And if you start adding lots of Netty handlers because you want to have clean separation of your business logic, then you can actually degrade the performance of Netty. And there is no way to save state. If you're doing some asynchronous job, probably you would like to save something for the future when you resume your pipeline, but you can't do this. And it's all because Netty is just for defining protocols. And it promises a lot, as I showed you in the beginning, but it's all this. It's only for communicating with HTTP, or maybe some custom protocol that you're going to design. And so that's our biggest mistake, that we lacked some experience, maybe opinions, and we didn't know how to install Netty properly in the bigger project. So let's talk about solution. And so we could probably use things like Akka, and it's doing good job for this microarchitecture. But in my opinion, it's very general framework. Again, if you have a problem and then you're starting using Akka, you have two problems. And I know it's not popular very much, but and basically you need to want using Akka. It's like, okay, it's cool, let's use Akka. But when I started to show Akka to my colleagues, they say no, we don't want to be part of this. And it's not elegant in pure Java, and we are using pure Java, so again, it's not the best fit. And I think the biggest issue is that in Akka it's hard to understand the flow of the events, and it's easy to create loops of those events, and single actor can process many types of events. So uh, you need to really remember by heart what the application is doing. So, and I think that's the biggest issue with Akka. We started using Areon, but I don't know if you know Areon. It's very good, but it's even more low level than Netty, and there's no defin. At least there is no definition of like idea of handlers. So you don't want to. You're not going to start some structure to put your business logic, and but you need to know what you're doing with Areon because you're on your own. And Areon is UDP based, and it's not a framework. It's just only for communication. But at least they like shouting to you. Don't use for anything else. Just like connect to pipes between services, and that's it, right? Uh, but we are very happy with Areon, and I really encourage you to have a look. It's very elegant, and it's very it's small library. So I think we are going to start using this more and more. Uh, Vertex probably would be the best choice for us. It had very good abstraction. It separates concerts with verticals, and we are using it. So we had some experience with Vertex, but I think we didn't go with Vertex because it felt like a big framework, and we didn't want to invest time with something that. Invest time in learning again something new. Mm, so you know, let's do build things from scratch. Uh, so I want to. I think I don't want to tell you that we are great, like we are a badass, right? That we know what we are doing always, because it's not. But I want to focus on the rules that are important here. We wanted to create a framework that are going to aid us in development. It's going to aid us in adding more feature faster. That is going to minimize the development cycle, and I don't have to worry about how it works under the hood. And so, uh, first of all, we want to give better structure to business logic. We would like to have some reasonable threading model, and of course decouple from Netty, maybe replace it with something else. And as a side quest, it was about remove redundant code, because each client needs metrics, needs circuit breakers, load balancers, and stuff like that. So we didn't want to repeat ourselves. I wanted to have some like something really nice and hidden by under the simple API, and have better protocol to because the one that we already designed was not that good. So there are few issues we wanted to solve. The most important for me was the business logic, and if we look at the application itself, so application logic should be a flow composed from stages. So more or less like in Netty, there are some stages, there are some steps to execute for each request. But instead, we wanted to be sure that if you start handling requests, you are going to produce response. You're going to go to the end of the flow and produce response or error. So there is no intermediate steps, because then you can reason what's going on in your application. And we wanted the flow to terminate, and that's also very important. And also we wanted we took like the idea of passing events in the framework, so like from Akka, like from Vertex, and it also helps. Now, about mm, thread model, we decided on a single thread pattern. because you probably so one thing is how your communication layer works, and the other thing is how your business layer works. So in the business layer, you could use some thread pools like Akka does, or you can do some fancy dispatching, like for example Hazelcast, because in Hazelcast, for example, each request has a corresponding key, and this key is always stick to the thread. Uh, but we wanted to be as close to this communication layer, and we want to leverage our net URL thread model. And with that, we were able to re-implement circuit breakers, because Hystrix is a great piece of code, but it's very heavy, and it was showing in all our performance tests in flame graphs. It was always Hystrix, so we just replace it. Now we are single-threaded. We can really make it simple. We have our own message accelerators, message load balancer, because we know that application is single-threaded. And also, we simplify our business logic, because it's now very simple. It's single-threaded. Of course, we had to create more objects with state, like clients. So each thread in the server need to have its own set of clients and or other objects that because you don't want to share state between threads. So we call it Stardust, and I've committed first code in late 2016. Later, my colleague joined, and he did the hard work. So I'm not the only committer. So there are a few pieces of its engine, and engine deals with dispatching events to the same thread. Right? It's the only piece that knows about thread. It knows about events. Engine knows about these flows of the stages. There is at least one engine per thread. So if you want to have logic that, as I said, I want to the flow to always terminate, or you get the error. So if you want to have different implementation, maybe like you want to fork your logic, you better create your two flows, two engines, and uh, and uh, and you don't want to mess logic between those two flows. Stages knows about business logic, so stages are a simple unit of business logic. There is only way to interact by events. One event can visit same stage only once. Again, this simple rule to make the make application even simpler. And stage accept event only once, so you cannot create any loops. This, the stage is just a function. You got the request event, and you produce event, right? That's it. You have context, but this context is not the net URL or other underlying framework context. Is just our context, so, and is always per request context. And what you do, you just emit new event, maybe this, maybe other. It doesn't matter. If you want to do some asynchronous work, you just need to extend different handler. You got your computable future. You are wrapping computable future with something we are calling receivable. And because we don't want you to think too much which API of computable future to use, maybe we would like to later interact with some other library like observables from Eric Java. So we want to hide this complexity under the receivable simple API. Configuration is like that. So, but as you see, this is the whole flow. We have those 10 or more handlers, and we know if we are getting a response, all of those handlers were executed. If we get error, maybe here, that's fine. And we are compiling this configuration in order to know that there is no loops or other things like that. In conclusion, we provide standard implementation, and that's very important because there is no code duplication. We provide standard implementation of mocks, and it's even more important for our development cycle, because we can create integration tests easier. And all you have to do, you need to put your developer hat and configure client server. That's it, and use our mocks. So right threading model is a key. I will show you why. It's because our max round trips has stabilized, and so that's important. They didn't drop, they stabilized. So you see, that's the max round trip latency between traffic and bidder. Uh, I told you that this is the important number, but we are somewhere here. Only minority of requests are responding with the higher time than 50 milliseconds. If we zoom in now, this 24 again max times. It's, you see clearly now that it's around 50 milliseconds, and it's stable. If we now go to triple nines, we are around 10 milliseconds, which is even better. If we see look at the double nines, we see that we are around 5 milliseconds. So this is the great achievement in my opinion, and more, we don't see any errors like timeouts, like flat, like back pressure, or circuited, and stuff like this. We need less machines. We were able to limit our machines from 20 to 4 in one availability zone. So that's also something. And the traffic increased from 80 to 150,000 requests per second in 2016. Right now we have like 100 something. So I think also is impressive. Uh, we managed to spot small mistakes. Probably every time you're rewriting your code, you're spotting some small mistakes, but it's a side effect. And of course, the Stardust configuration is not foolproof. You need to know what you're doing. That's why probably we haven't open sourced it yet, and I don't know if we're going to do this. And we are not depending on any framework like Vertex. We are controlling. We don't. We can switch the communication library very easily, and we actually control the resources flow and stuff like that. So we don't have to learn new stuff. We just try to do our best. So takeaways. You need to understand your problem first, and then probably somebody said earlier in this conference that you need to look around and to understand what other libraries, frameworks are giving you. And if you still think that it's not the best fit for you, probably you would like to learn from them and just get the best part. And I think the biggest challenge is to focus on your business, because it is all about, you want to improve development cycle, you want to be able to deliver as fast as possible. Everything else is just distraction. So if you struggle with your communication frameworks, that's bad, right? You just want to sit and write code that deals with the features, new features. Uh, and choose right micro architecture in your microservices. Haha. And that's all. So thank you. So I'll be around in this table if you have some question now, I'm happy to answer them. Yeah, okay. Do you have the microphone? Because I hate Eric's Java. No, I wanted to put it on the slide also, but I think I feel like Vertex is closer to me than Eric's Java, and I don't know. I feel like it's not my framework. But I know what you're asking, probably because you have those composable flows and stuff like that, right? Yes, yes. But we also had a lot of trouble with Eric Java. There are other teams which are massively using Eric Java. They were complaining about that. So, I am not expert on Eric's Java. So, but like I said, I feel like it's not the framework for me. But I understand the concept, right? Yes. Yeah, we are using Netty or Iron depending, but we're still using Netty because it works. As I show you, the benchmark are great, and Netty basically works, and there is no other alternative for Netty. It's all about composing Netty with higher level abstraction for your business, right? So that's basically the 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 point of the of this presentation. Uh, Yeah, of course, the Akka, Node.js, Netty also gets ideas from Node.js, right? So, we have multiple because we are using all the cores, and but basically want to run each request in the single thread, right? And then we don't need to think about synchronization and stuff like that. That's why we don't want to run business logic on the thread pool, because then you don't know, after coming back from some asynchronous job, you don't know which thread we're going to continue, and that's why we ended up with this one thread pattern, right? The same thread pattern. Okay, right. If I was arguing earlier about that, and I think yes, I think that Akka or Vertex, maybe Akka more because it's Akka is so powerful, so general, in my opinion, and probably Vertex less because maybe you could just have these verticals and y- it maybe it's lacking configuration. Maybe there is an lacking additional structure on top of the vertex that will just keep order of those handlers, right? In my opinion, that's why we did what we did, because we wanted to be sure what the application is doing, and we are going to our configuration files, and we see, okay, that's the handler that's in this order, and we know, for example, if we found some log that says that something's wrong in this handler, we know what was the previous execution, right? And I think it's very important because you don't want to lose time. And in Akka, usually you are just trying to you need to understand what you need to remember what Akka is doing, or or you need to look for it. Yeah. Mm. Okay, yeah. So I'm not saying that it's wrong, using Akka vertical or something. We just identified problems, and I think we wanted to address them, and that's all about it. If in near future we want to change it because what we are doing is we are going to find that it is wrong. Probably we are going to switch to Vertex maybe, or maybe to some other battle-proof frameworks, right? So okay, thank you very much.